Our next step in this stoichiometry process is to talk about what happens to a gas in all of these reactions, because gases, they're odd. I mean, trying to actually deal with gases, well, first of all, you can't see them, so they have such, and if you actually have a mass of them, it's so small that it's very hard to deal with in the lab. So in many cases, volume is a way to deal with gases. But we have to dictate what the conditions are for that volume, because let's think about a gas in, let's say, a balloon. So here we have our balloon. Now, what's going to happen to that balloon if you put it somewhere where it's cold? Think about what's going to happen. What are those gas molecules going to do as the temperature decreases? They're going to slow down, right? Because molecules slow down when the temperature is lower. So if the temperature is lower, the molecules slow down. So what's going to happen to the volume of that balloon? It's going to shrivel up, right? It's going to decrease. So it's going to be smaller. What if you take that balloon and you put it somewhere where it's really hot, like a really hot car? Well, in this case, the molecules, because of the added heat, they're going to move faster and faster and faster, so that's because the temperature is going up. And so that means that balloon is going to be bigger until, of course, it might burst. But so because of this fact that volumes are so dependent on temperature and pressure, we actually have to, in order to set any equivalence, like we did with 1 mole our molar mass, we have to set the temperature and pressure. And so our rule is that 1 mole of any gas at standard temperature and pressure has the volume of 22.4 liters. So let's break that down. First of all, standard temperature and pressure is abbreviated STP. In my day, it was Stone Temple Pilots, but no, it's actually standard temperature and pressure. Now what is standard temperature and pressure? Standard temperature is 0 degrees Celsius. That doesn't look very good. Let me erase that. We'll undo that. 0 degrees Celsius. Okay, so right about freezing. And pressure is 1 atmosphere, which is, that's the pressure on you, the air pressure on you if you're at sea level. So if you have those two defined things, the standard temperature and the standard pressure, then 1 mole is equal to 22.4 liters of a gas. So think of like a 2-liter bottle of pop. Think of that, okay? So it's about 11 of those 2-liter bottles of pop. So take that volume, just so you know what my drawing is. So take about 11 of those, and that's the volume that we're talking about. And that's how much 1 mole of gas is equal to. So this is our new big equivalent that we're going to use. 1 mole is equal to 22.4 liters. 1 mole is equal to 22.4 liters. And this is for a gas. This only works for gases, and it only works for us if we're at STP. So let's see how we use these. Okay, so we have a equation that's everything is gases here. Here is methane, which is, of course, like our Bunsen burners, and it burns in oxygen to form carbon dioxide and water. Okay, so let's start with this step here. How many grams of methane are needed to completely combust with 112 liters of oxygen at STP? Okay, so we have liters of oxygen. First of all, is that a gas? Yes, that's a gas. Do we have it at STP? Yes, we do. So now we can use this equivalent. 1 mole is equal to 22.4 liters. Okay? So now we are going to set this up exactly like we have done all of these we have in the past. So we have our given is 112 liters of oxygen. What are we trying to find? Grams of methane, which is CH4. Okay, so we're going to be turning liters of oxygen into grams of methane. Okay, our first step, and just like in the past, we were dividing by the molar mass. This time we're not going to divide by the molar mass, we're going to divide by liters, which is 22.4. Because 1 mole of O2 is equal to 22.4 liters of O2. Okay? So now we're going to do our next step exactly like we've done in the past. We're going to turn oxygen into methane. So what is our cookbook step here? What is our ratio? It is a 1:2. So 2 moles of O2 is equal to 1 mole of methane. How about I actually use the abbreviation instead of that? That actually works a little bit better. Okay, now our very last step is we need grams of methane. So to get grams of methane, now we're going to do moles to grams. And how have we learned to do moles at grams? We multiply by the molar mass. So 1 mole of methane is equal to 16.05 grams of methane, because that's the molar mass. And so when you run through this, you are going to put in 112, and then you're going to divide it by 22.4. Then you are going to divide it by 2 and multiply by 16.05, and you should get something like 40.1 grams of methane. That's how much methane you're going to need in order to combust 112 liters of oxygen. Okay, so that's how we use liters. Now you can use it, and you can use it also to figure out how many liters of things that you need. So we want to know how many liters of carbon dioxide that would generate. Okay, so we're going to start with our same. We have 112 liters of oxygen. That's what we started with. Again, first thing, we got to get to moles, and there are 22.4 liters of oxygen in 1 mole of oxygen. Now we need to check our cookbook step here. This time we're turning into carbon dioxide, and it's a 2:1 again. 2 moles of O2 is equal to 1 mole of CO2. Now, our last step here is to really pay attention. What is it asking for? Oh, it's asking for liters of carbon dioxide, and carbon dioxide is a gas. And so we can use the same equivalent that we did before. 1 mole of carbon dioxide is equal to 22.4 liters of carbon dioxide. And so now if we look at this very carefully, some things cancel out to make this pretty easy. Okay, so we have 22.4 here on the bottom and 22.4 here on the top. So those two can cancel. So essentially the only math you're doing is 112 divided by 2. So that's all you have to do, and that's 56 liters. Okay, but that is the setup. Okay, go ahead and give the ones on this backside a try. Again, if it's at a gas, at STP, standard temperature and pressure, which is 1 atmosphere and 0 degrees Celsius, then you can use this equivalent that 1 mole is equal to 22.4 liters. All right, good luck.